Hi, we are doing our assignment number 2 on FitRec dataset that we collected from our class website, and we're titling our assignment number 2 as FitRec dataset predicting from activity telemetry. So our summary of our dataset or our assignment is that we're going to be creating machine learning pipelines to predict a categorical target, like a sport, from session level activity data. It starts by pre-processing the data, converting list-like items into series into a statistical summary per session, like heart rate, speed, etc. Then encoding categorical features and removing columns that cannot be directly used in the model set. Next, it performs dimensionality reduction using singular value decomposition to project a high dimensional feature into lower dimensional space. A random forest classifier is also trained in the reduced training data with hyperparameter tuning performed using validation set to identify the best model. Finally, the best model is evaluated on test set to assess predictive performance with outliers and unusual feature distribution considered during pre-processing to ensure model validity. The relevance and practical applications for this assignment could be that in successfully predicting the sport a person is performing has commercial value, an accurate prediction could enable targeted advertisements for the specific sport, allowing companies to market relevant products or services to users based on their activities. We start our assignment by importing necessary libraries and functionalities and setting default variables. We've also created some helper functions on our own that helps us distribute and plot graphs much more in a unified way. And we'll also create a load function that creates our loading of our database or data sets a lot quicker than it regularly is in high volume files like 6 GB or higher. We're just getting some data sets from the data frame to see like, hey, what is the data sets looking like, and just trying to get a quick visualization of the data sets. We do a quick info to look more into the data sets to figure out what the columns are, what the values are, data types, to figure out, hey, is there any null values, or missing something, what's going on with the data sets. Then in order to figure out exactly what type of data types we have, we go through much more in-depth analysis of the columns to figure out, hey, we have got ND arrays, we've got strings, integers as part of our data sets types. So we go into talking about what is our predictive task that we're trying to get here. We're going to talk about how we describe our model. We talk about what the baseline is that we're going to be using, how to improve those baselines, and how do we assess those baseline and our improvements, and how do we talk about our predictions and what happened with our results. So we're going to be starting off by our baseline is going to be using majority class baseline and random guessing, and majority class baseline will be always predicting the most frequent classes in the training set. Pretty simple as that. And random guessing, we're going to be utilizing random chance of guessing what do you want to just randomly guess based on what's out there. Then we're going to try and improve those baselines using logistic regression and random forest to improve our performance over the baseline models. And then we'll be doing hyperparameter tune-ups based on the model that performs better. So whether it's logistic or random forest. Here, logistic regression, we'll be using this to predict the sport based on linear regression of the data, and then random forest we'll be using to give more flexibility to predict multi-class classification problem. This will be more appropriate over the regression model since our data is not continuous. And we will be assessing this prediction based on the consistency across data splits, comparing the validation and the test accuracies to make sure there's no overfitting going on. And then we'll also be doing some error inspection as well. So where do we get this data from? Again, data was collected from the class site that the professor gave us. And the data that we chose was already pre-processed by making sure that there's no inconsistencies between data sets, there's no abnormalities, and all the z-scores were appropriate. And again, because it's z-score, a lot of our values are both positive and negative, which we'll see later. And on top of that, we do some of more statistical analysis per row to figure out what the statistics were for that workout session. Then we do much more analysis on the column-based statistics to figure out, hey, what is going on with the entire data frame of our columns? And we see that there's a lot of consistencies, that we have a lot of extreme outliers going on. We can see that there's a lot of third quartile is ranged between here, different number values that we will see down in the plots. But again, we've got a lot of extreme outliers in here that Haley will talk about later. And we start plotting our diagrams using our helper functions that we've created. So we have much more unified way of seeing and what our plots look like. So I will have Haley talk to us about the plots.
So the first set of plots that we make are some histograms from some sample variables in our data set. We decided to plot heart rate mean, target heart rate mean, and then the standard deviations of both of these variables. For the mean distributions, both of these variables are normally distributed, having centers around a z-score of 0 for heart rate mean, and then a center of 140 BPM for the target heart rate. And then the standard deviation distributions for both of these variables are right skewed, um, indicating that most workouts have lower variability in heart rate, in essence, smaller standard deviations, implying that most people maintain a fairly steady heart rate throughout their workouts. And then the right tail indicates higher variability in heart rates, and this could be due to more intense exercise bursts, potential measurement errors, or outliers. The next set of plots that we made were scatter plots, trying to understand the relationship between different variable combinations. And the three combinations we looked at were heart rate mean versus derived speed mean. Between these two, we didn't see any obvious correlations between the two variables. Then we looked at heart rate mean versus altitude mean. Again, we didn't see any obvious correlations between these two variables either. And then heart rate mean and distance mean. With this set of data, we started to see a more negative correlation with some of the more extreme higher values of distance mean, ranging from 200 to 800. We see that as the distance increases, the heart rate mean decreases, but there's really just not enough data points to make a full conclusion on this. And then the majority of the data doesn't seem to have any correlation. The next set of plots we made were categorical box plots looking at the heart rate mean, derived speed mean, and altitude mean based on sport and then by gender. The first one, looking at heart rate mean by sport, some conclusions we draw from this is that based on individual points, the highest heart rates are seen with running, biking, and mountain biking. And then the highest median heart rates are seen with sports such as sailing, aerobics, and treadmill running. And then the lowest median heart rates are seen with sports like golf, table tennis, and gymnastics. The next box plot we made was looking at derived speed mean by sport, but we noticed we had a very high outlier with this data set, as Mahir mentioned earlier, which prevented us from being able to visually determine any trends with this variable. And then the next plot that we made was looking at altitude mean by sport. With this, again, based on individual points, some of the highest altitudes we're seeing are with sports such as biking, running, and mountain biking. And then the highest median altitude we see is with downhill skiing. Next, we created box plots looking at these variables categorized by gender. So with this one, we see that the highest median heart rates are seen in women compared to men. And then the next box plot is again looking at drive speed mean, but we're not able to derive any conclusions from this because of the presence of that outlier. And then the last plot is looking at altitude by gender. With this, we've concluded that there are just more variations in altitude means seen in sports sessions that are done by men compared to women. Next, what we did was investigated that outlier from the derived speed mean, and we decided to actually exclude it from for further analyses of this data set. And then we recreated those categorical box plots looking at drive speed mean by sport and by gender. But then we noticed that we had additional outliers in this data set that prevented us from making any conclusive um, conclusions about these categories with derived speed mean. The next plot we made was looking at a correlation heat map to better understand what variables may be correlated that we didn't see with our initial scatter plots. And from this, we concluded that the highest positive correlation we see is between latitude and longitude standard deviations, indicating that as one variability goes up, so does the other. And then the highest negative correlation we saw was between derived speed standard deviation and derived speed mean, indicating that as the derived speed mean decreases, the variability in the derived speed increases. And then for the negative correlations, to understand what the relationships are between the two variables, we recreated some additional scatter plots to confirm those correlations. So the first one's looking at the derived speed mean versus its standard deviation. And then we're also looking at some other negative correlations between derived speed mean and distance mean in the second plot, and then versus distance standard deviation in the third plot. And this is showing that as our distance mean or distance standard deviation increases, the derived speed mean decreases. And then the last set of plots we created were these plot line correlation graphs to better understand what the original structure of this data set was. For each workout session, a time series is collected for variables such as heart rate, altitude, and derived or a distance. And so for a single workout session, we decided to plot these time series for each of these variables just to get an understanding of what the data looks like. And then moving on to our modeling, before we applied any machine learning algorithms to this data set, we did some additional data cleanup and feature engineering. The first thing that we did was remove those additional outliers that we saw in our categorical box plots for derived speed mean, and then some additional outliers from distance mean. And then we one hot encoded our gender variable, and then encoded our target variable sport. And then we double checked that our data set still didn't have any NA values before splitting it into our X and Y data sets, which is our feature set and label set respectively. And then now we'll get into our machine learning modeling.
So before we split our data, we have to check before we split our data into train validation, we have to check out something. So we noticed that there are multiple sports that only have one or two record inside in the data set, which there will be an implication for it later. We split the data set three-way: train, test, validation, and test, just for additional assurances. And again, we check again to see if there is any sport that is missing from our train set. And we saw that there are instances where there's only one record of the sport, such as badminton and sailing. And there are also sports sport that are missing from the train set, such as rugby and kite surfing. So so before we put our data into the model, we want to reduce the dimension by using SVD. The dimension that we chose is 15, and the eigenvector are extracted from the train set. So, and we use those eigenvector to do matrix multiplication on the train validation and test set. So the advantage of using SVD is that we can reduce computational time and cost, and also can help the model to generalize better. But the disadvantage is that the SVD could be inefficient with very large matrices, or uh, and we also must ensure that we're using the eigenvectors extracted from the train set and not anywhere else. So so again, like we mentioned earlier, we have two baseline model: majority class and random guessing. Let's go through the performance. We measure performance by accuracy, which is just the portion of correct predictions, mean square error, root mean square error, and mean absolute error. So for the majority class, we see that the model has an accuracy score of 0.468, And the random guessing has an accuracy score of 0.03. So the random guessing, as expected, does very, very poorly at only 3%, but the majority class actually much better at 40 something percent. And then now we want to pick some model some actual data machine learning model to help with our prediction task. We chose two. We have logistic regression at 0.45 accuracy and random forest at 0.82. So the random forest give much better accuracy score compared to everything else, and that is what we choose to focus our tuning effort on. Is we just training the model here. Let's go talk about our best model. The best model that we found has the parameter of criterion to be entropy, max step of 50, and n estimator to be 200. And the test accuracy for both the validation set and test set is about 0.82, which is not much, unfortunately, not much of an improvement from what we have originally. This is our confusion matrix, where we observe there are columns with zeros in them. That means that spot is just not visible in our validation and test set, and which we have discussed before. So this data set has been used by the professor in his study to he used a different method called long short-term memory to build a sequence of information where he's predicting the heart rate, and then build recommendation to user who want to achieve that similar heart rate. For us, we are using a more traditional supervised learning task where we are focusing on one label and a non-sequential classification task.